So let's say you have 5 minus 2, right? So you have something like this, yeah?
Yep.
All right, so you start here, you just go through all these ones, you go through the 0, you go through these ones, there's gonna be an empty sign here. So once you encounter the empty sign, you put an X here or whatever, it doesn't matter what, right? And then you go back, and you basically start again. So you're in the second state, whatever you call it, right? So we go here. Once you encounter the first one, you replace it with, it doesn't really matter, it could be 0. And you bounce to the left, 0. And you go back to the right, 0. Back to the left, 0. Then you experienced X. You replace that with empty, right? And then you replace every single 0 on your way back with empty. So you get empty, empty. Well, you know what I'm saying. Empty, 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 empty.
Yeah,
go back to the beginning, done.
Yeah, that's where that adding the symbol at the end before the blank will trigger that to help you recognize when you've finished.
Yeah, because you have to recognize when you finish bouncing, right?
Yeah.
I mean, the other way would be to basically not add it and do it until you hit the empty sign. You cannot have the X. You don't really need that. It's just optional. Just like adding them. So you can do the same thing without the X, right? So you start, I'm gonna make it bigger. You start here, you go to the 0, and then you bounce from this moment on, you bounce right and left. So you counter a 1, you replace it with 0, and replace it with 0 here. Again, go to the right, replace it with 0, replace it with 0. Go to the right, you experience the empty sign, therefore you know it's the end of the string. So now you go back to the left, removing all the zeros, go to the beginning, that's it. So it's pretty simple, actually.
I guess whenever I was trying to draw it out in states, I wasn't able to actually draw it out in states, if that makes sense. And then create an actual lambda, or not lambda, just an actual transition function out of it.
So if you start with S0, S0, 1, that would be what, S0, 1, right?
Yep.
Okay, and then S0, 0 would also be S0, 0, right? And then the S0, let's call it lambda, right? That would be an S1 lambda left, right? So then we go to, we have to locate our 0 right now. So we, what the hell is, oh, lambda, yeah. Lambda, that's probably not the best choice of character. So what can we use? We can use underscore, right? Or an empty character. So then we have to go back to that middle 0. So we have to skip through those ones. We do S1, 1L. And then once you hit 0, that's when the fun part begins. So this is when you start deleting numbers, because you know you're in the middle. Actually, you don't even have to go all the way through. We can make it shorter. Okay, once we hit 0, let's make it shorter. Once we hit 0, we start deleting everything. So we go to 0. Let's change that to S1. Beautiful. Okay, so you're in S1. When S1 encounters 1, it's going to change to the carriage return. So it has to replace it with 0 and go to left. And if S1 encounters 0, that means it's jumping over zeros, then it basically continues. Right? And then if you're in S2, you will only encounter zeros on your way left. So,
I don't even understand how you're able to do this without drawing it out.
That's what I'm trying to do right now.
Yeah, I'm trying to do it too, and it's not working out.
Okay, hold on a second here.
Yeah, let me write down what you've got. So 0, 0 to the right. 1 goes on 1 to 0 to the left.
It's going to be.
Okay, I think I see something here. Okay, hold on. So if we go
And so we're deleting, and then at some point we're gonna, it's not S0, that's S1, 0. Okay. So then we're gonna hit, yep. Okay. Yep, all right. So if you're an S1 and you encounter this thing, that basically triggers the end of everything. Yep. And then S3 will only encounter zeros. You don't need that. So it's going to be this.
I think you could do this in 3 states. Hang on a second.
Yep. Actually, 4
Or,
states.
yeah, maybe four, because you have to end it. Yeah.
And simulate it now. Okay, so let's try now. We start with 0. When we encounter 1, we go through it. So we're going here 0, 0, 0, 0, 0, 0. Then we encounter 0. We switch now to state 1. I'll put the state here. Okay, so we're in state 0, then we hit that 0. So rule in line 5 kicks in, and you basically switch to S1, right? So we go to S1, you're now here. In S1, you found 1, so you replace it with 0 and switch to S2 and go to the left. So we go back here. In S2, when you encounter 0, you leave that and you go to the left. We do that. When you encounter 1, you replace it with 0, go to the right, so basically here, and switch back to state S1. So we're in S1. What?
This is insane. It just works. How did you just do this?
Yeah. You're pissing me off, Tom.
Okay,
This
so
would've
let's just finish this shit.
3-hour-long question.
So then 1, you replace that, you go back to S2, you go to the left, boom, 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 hit this one, replace it with 0. Okay. We replace it with 0, and now we do our S10 right again. So we are here, boom, 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 go to the end. So we're in S1, we're encountering the empty char, we kick S3 and we go to the left. In S3, whenever you encounter a 0, you replace it with nothing. So we just delete, 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 delete. Okay, when you encounter 1, you just keep it as it is. And when you encounter an empty character, you go to S4 and basically end here. And that's when you terminate. Yep.
That
Yeah.
is insane.
I missed the Q1 zeros. I had my zeros going a different way. This one's way better. Well,
I almost feel like it is better just to not even mess around with the diagram. Just look for the states themselves.
Yeah, I always think about it in terms of a header, you know, that just goes left and right. It's just easier that way. If you're trying to like algorithmically explain what you're trying to do. So it's kind of, I think it's easier that way. I wouldn't draw it out. If I draw it out, I'd be like, it's just a bunch of, you know, lines and bubbles.
Those lines and bubbles are the only way I know how to do this.
Well, look, to each their
Yeah,
own.
same here.
It's pretty much the same thing, right? It's just a representation. This is just easier for me to read, but if you want to draw it out, you can draw it out.
Oh no, it's easier to read this way, but that's not the way we were taught, so that's not how I do it. It's a thing
do you mean?
of monkey see, monkey do it.
Hold on a sec. What do you mean taught? She didn't. There's not an actual way of
Good
doing
point.
it. Yeah.
Good point.
Like
The
in
way
the book,
that the
they're saying,
textbook-
"Oh, this is the algorithm. Why don't we just assume that this is the solution, and now we're going to show you for the next 3 pages how it is the solution." Mhm.
Right. Ridiculous.
Yeah.
But Matthew, do you understand that? Do you agree with this? Like,
Yeah.
are you okay with that?
No, I definitely, yeah, I get it. I just don't understand how you can come up with it that fast or like that, but
Yeah.
It's just if you try to code it low level, this is pretty much what you would do. So you can think of coding that in an assembly language. This is pretty much what you would be doing.
Interestingly enough, seeing you do
Just-
the process of all this actually did help me to understand it a bit more.
just code it in assembly, guys.
Yeah, just do it.
Oh yeah.
Well, not coded it, but just try to.
I know.
You know what I'm saying?
you saw my post, Tom. I never want to touch assembly language.
Yeah. So, well,
Good stuff.
you pick computer science, which is actually all low level, isn't it? So
Yeah.
Yeah.
Yeah, it's true. If you think about it in terms of what the header is always doing. And keeping track of what your delimiters or your ending symbols, your boundaries are, those sorts of things are what they can help you trigger to another state.
I mean, what I usually do is I start with something that's not optimal. Like I added that X first because I didn't realize you don't actually need it. And then you remove those redundant states and delimiters and you end up with something simple like that. I think that's the easiest way of doing it.
Yeah, that makes sense. Sort of like refactoring. Oh, that's really good.
Yeah. All right.
I'm glad you're on our team.
I know, right?
Now make one for exponents. X to the y power. Yeah, do that.
Say that again. X to the Y power.
X to the y power, yeah.
Don't
So in this
tempt them.
case, 5 squared. Do it. 25 in unary.
Say one minute.
I'm kidding. You don't have to. You don't have to. Just trying to think of the most difficult process that it would take. Oh God. That just means you do 5 for every
Yeah.
number there is.
You just basically translate this to 5 plus 5 plus 5 plus 5
Plus 5 plus 5. Yeah. So for each one, just add 5 to it. That's actually really not too bad.
It wouldn't be too bad. It would be messy with one tape though. This would be
Yeah.
much easier with 2 tapes because the number 5 itself, you would
And
put
in
it on the
that
second
case-
tape.
And in a case like that, would you then input it as 502 or would you input it as 5051s? Because
What? Say that again.
wouldn't that be?
if
So
this is,
in order to tell your tape what to do, like wouldn't you have to do like 5 ones, then a 0, then 5 more ones to make it 5 squared for input tape, or can you get away with 2? Can you do it with 2?
you do 5 to, this is a powering machine. So basically
Yeah,
what the arguments mean is the characteristics of the machine. It has nothing to do with the tape itself. All right, it's like the formula that you pick on the calculator. Digits 5 and 2 are meaningless. They only become, their value comes from the whatever instruction you give to the calculator. So this is a perfectly fine notation. And we know there is a Turing machine to actually do that because computers can do it, right? So.
Okay, well, wait, let's stop and explain this to me a little bit more, because in this case, I'm thinking of how would you convert that first one that's in the 2 side?
Just one there.
Yeah, like like if I'm looking at that as input and I'm saying, okay, how would I get my Turing machine? How would I do what you just did with our last problem as a function and turn that into 5?
Well, here's how I would do it. So
I mean, I guess it is like what you just said, it's whatever instructions you give it, right?
I'm not going to do the notation because for multi-tapes it's a bit messy, but okay, so let's say we actually do have 2 tapes. So first I would retype, I would copy this value into the second tape because we needed we'll find out why in a second. Then we can get rid of one of the powers because 5 to power 1 is just 5. So we really start powering from 2 and 3 and so on. So let's just get rid of one of them for clarity. And now you start basically the powering phase. So what you do is you go to the 0 and you duplicate this 5.
Oh yeah, okay, I see. Okay.
And you remove 1 from here, right?
Yeah,
then you duplicate 1 more time. You remove 1 from here, and so on and so forth.
Yeah. It's about it's how we instruct each state to do.
So you do this,
yeah.
And once you get rid of all of those ones, you remove the exponent.
Yeah.
And if you removed all of them, then you're done. But if it was 5 to power 3, then we would have 1 more here, right? So then you just repeat the process.
Yeah.
It'd be another 5 on the second tape.
It'd be
right?
another 5, yeah, and then you just do the same thing.
Yep, I like that.
I don't, but yeah.
I mean, I like listening to Tom break it down.
Yeah, so powering is not too bad. But again, that comes from the fact that powering is just multiplication, which is just addition, right?
Right.
Yeah.
Certainly is.
And what I meant by my, when I said that the numbers are just numbers, unless you actually feed them to machine, is like, let's say you have arguments to your function, power 5 and 2, and then you have multiplication 5 and 2. This would be the same tape, right? They're just fed to different machines.
That's right. Okay. That's what I was getting convoluted in thinking about that. And I'm realizing now where I was not thinking it correctly.
It's the role of the machine to make the interpretation of what they actually stand for, those numbers in this particular instruction. All right. So what we're doing, where's the study guide for this thing?
Okay.
The announcements? Oh no, it's in the module, isn't it?
No, I think it was the announcements.
Yeah, it's not in the module, so. Office hours, final exam day.
I'm gonna write this down real quick while you guys are looking.
So give a DFA that accepts a particular language. That's pretty easy, right? That's what we did.
Yeah.
So we should all be good with that. You should be able to specify the set of Q states, the input alphabet, the initial state, and the set of finished states. You can descriptive state names, but you're welcome to use Q0. Oh, that's the instruction.
That's a part of
for
the DFA. Yeah.
Beautiful. Okay. You should
And
be able
so
to
is the
define
next.
it.
Yep.
It's actually not bad. Actually, this study guide, if she's going to just follow it to the letter, it's not going to be too bad.
Maybe.
All right, give a context-free grammar for the language. Again, there's not much you can actually learn here or study. You have to see the grammar, right?
Yeah.
Okay.
That'll be the gimme, as she called it.
Use properties and effects related to context-free languages. Yeah, so that's what that's where we wasted time on the last test on this bonus question. Because we didn't actually have to give the full grammar for that. We could just say,
Right.
oh, based on section 8.2 on page 157, I conclude that.
I want to
Because
know
we
how
all
many
have
of y'all
that.
are going to pull up page numbers on the exam. I think
That'd be so fun.
I'm not.
it's really impressive.
As we saw in question 3 and 10.1 on page. Is
Yeah,
that to prove
2001 edition of this book.
Yeah.
Okay, so really we just need to know, I think what she's saying here is we just need to know which, what do you call it? Which functions the context-free languages are closed under, yeah?
That and whatever that theorem 8.5 was, where it's like let me find it.
Just gonna open the book and put it here.
Closure under intersection. Yeah.
That is the same thing. That's what I just said.
Yeah, I'm trying to find the exact name that I called it, but apparently I didn't reference it.
Okay, let's remember what is closure under regular languages. What is that? Union, intersection, complement. Is that right?
I'm just gonna put it here. I just wanna, that's what I wanna do.
Okay.
So she says it's section 8.2.
Yeah, hang on, let me make sure I got this right with regular languages too.
So CF closed under union, concatenation,
Star closure, right?
and star. Yep. That's it. That's it. And regular. Is there a separate section for regular languages?
Let's see. Yeah, let me see if I can tell you. Hold on a second here.
What was the regular language anyway?
Come out the closures.
No, what was what's the regular language?
Regular
Finite.
languages are limited, like they don't have, if I'm remembering right, like you have your clean star.
Google that shit. Regular language. Let's see
They're
what it is.
finite, I know.
Yeah,
Can be made with a DFA or NFA, something like that.
Regular language is conventional. A formal language that can be expressed using regular expression. Okay. Oh, okay. So they have to, if that's regular expression, they could be NFA or DFA. Yeah. Because regular expressions can have stars and shit like that. Oh, there you go. A regular language can be defined as a language that is recognized by a finite automaton. Okay, so regex or finite automaton. Fine. And she kind of hinted today that we're going to be using the. It wasn't union, was it?
Is
Was
the yeah, it was the
It was
intersection.
union.
intersection, yeah.
But hold on a sec. It doesn't say anything about the intersection.
Yeah, so there's
that-
another one, Tom. There's another theorem,
Oh, yeah, I see that.
8.4. Or
It's
excuse
8.4.
me, 8.5. 8.5.
Ah, I knew it. Yeah.
Yeah.
So when the in 17 and 18 questions use them, I was gonna ask her, but she just kept
No,
making me more confused each time.
I think she kind of hinted that we should remember that one.
Yeah.
Which one now? Say again.
So that's CF times reg gives us CF. Yeah. Yep, that's basically what it says.
CF times regular expression?
The and.
That's and.
Yeah.
Sorry, the and. There you go. That's actually a better idea. Yeah.
Oh, you're using the and to represent like intersection?
Yeah.
Yep.
Okay, gotcha.
Okay. Is there anything else in this book?
No, there's nothing else.
I mean, there's some shit that we might need to use, like given a context-free language, there exists an algorithm for determining whether or not it's infinite, but I don't think they're going to throw it on us. Not after the last 3 days of office hours. You should be aware that if she wants to see this class get anywhere, then
Watch, we go into the test and like 3 of the questions are missing. It's only 7 questions total now.
yeah.
They're just all extra credit.
Yeah,
Oh, that'd be great.
need it.
I'm actually going to save that file before I lose it. So that's COP4420 final.
Excuse me.
All right. Give a deterministic Turing machine for a particular function. That's what we just did, right, with the subtraction.
Yep.
Yeah.
So that's cool because it's deterministic. I'm actually glad we didn't do the non-deterministics because they're a bit freaky. Like, I'm guessing this, but I cannot guess that. All right, and all these other points are just bullet points for this shit, aren't they? Where's my browser?
Crap.
Here. Should be able to specify the Q set of states. Yep, you should be able to define the delta function. And you should be able to explain how a Turing machine works in words. Okay.
Yep.
I'm gonna use that stuff that Matthew used in his post the other day. I actually put that in my homework as well. What was that first sentence? Yeah, I just did it for shits and giggles. Hold on, it was, oh yeah, the question number 5. I said, this is straightforward and uses a variation of algorithm presented on the
I copied that straight from the book.
Yeah, I know.
Yeah.
But she liked it so much, I was like, okay, I like it so much, there you go. This is straightforward.
Matthew's like, it's just so easy. I can do this.
You know, if we don't know how to answer something on the test, you can say this is straightforward and the answer is in the book.
No, yeah, it's trivial.
Yeah,
The proof is trivial. We know.
Proof is trivial,
Easy.
therefore we're going to leave it to the grader.
We'll leave it great. You know, I might have to do that if I get really pissed off on one.
Or the proof is tedious, therefore we're going to leave it to Dr. Burns.
Just need proof forthcoming.
All right, now goes the fun part. Demonstrate that the modified version of the standard Turing machine is the same computational power as the standard Turing machine. Yeah, that's very useful skill set. That's what I do every single day.
Of course.
Excuse me, sir. Did you know that if we limited that Turing machine, it would still perform the same function? All right, section 10.1. So what are the variations? Equivalence of classes, blah, blah, blah. Stay option. I mean, this is actually quite easy. I'm going to put it here. So stay, we know how to simulate stay, right? We're going to add an extra state or something like that. So stay is basically left plus right, or vice versa. Agreed?
Yes.
Okay.
Nice.
So that will stay. What's the next thing?
Because what stay does is it actually adds transitions. It says move right, then move left, or move left and then move
Yeah,
right.
that's something that just cancels out, and that's your state.
Yeah.
The next one is semi-infinite tape. I didn't read about that. Many authors don't consider model blah, 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 blah. What's that shit?
Means that it limits the left side. It like makes it 2 that have infinite right sides, but the left side gets cut off.
Yeah, I mean, you can also,
She didn't ever talk about that one, so I'm kind
Yeah.
of like, I think we're good. I think we should stick to the halting.
Yeah, okay. All right, the
Because it
next
seemed to
one.
be what she focused a lot
Let's
on.
just go through everything in this chapter and then we'll decide which ones we stick to. The offline
Yeah.
Turing machine. What's an offline?
It like saves it in its own like file. It has like an input file and it saves crap and you can.
Temporary storage.
It's not
No,
great.
it's current input file.
Another
Yeah,
thing she never mentioned.
I don't understand any of that, so I'm just gonna leave that. So let's just assume that stay is going to be the only option here. I mean, I'm gonna add it here, but I don't think it's of any significance. All right. Show that a language is recursively enumerable. That's our favorite one, isn't it? 11.1.
Oh, that's fun.
I mean, what she did today, and I was driving, so I only saw it on my small screen. That was actually pretty cool. I really like that part. So what she said is, if you can produce a context-free grammar, then you can represent that grammar as a tree. You can sort of show the derivation tree for that grammar from one state to another, right? And then you build this whole infinite derivation, and then you do a BFS on that, which kind of represents your enumeration. And then sooner or later, you're going to hit every word. Well, not every word, but sooner or later, you're going to hit the word that you're looking for.
Right,
So
and that totally changed my way of thinking about it, because my way of thinking about it was the proper enumeration. You know, you start with your smallest, like if you have language A, B, you're going to start
Correct, but
A, then B, or A and
how are
B.
you gonna show that? You're not gonna show
Right.
that. Right? We see those machines are black boxes for us. We just say this is what they spit out, right?
Yes.
But we're not really gonna ask the questions how, because that would be problematic. So I think what she's going to effectively want us to do here is somehow reduce that into a context-free grammar. And then from that, you produce the derivation tree. I don't know if that's the correct name. I just called it like that in my head.
Mm-hmm.
And then from that, you do the BFS, and that gives you the enumeration. Enumeration, i.e. given word W will appear at some point. Agreed?
I think one thing that we do need to keep in mind with that chapter in specific is that is the theorem 11.4. It might be that, or it could be a lot easier. 11.4 just basically says a complement, a recursive language complement is also recursive. So
No. It says that if L and its complement are enumerable, then they are also recursive.
Right, but let me find the question, because she went over one of these on the first day and it was
I'm looking
really
at it right now, so I'm going to put it here as well.
Is that the
So-
one that you posted on our board?
number 5, something like that.
Let's try. Okay, so she says that
Yeah, that's it.
if L and L minus are enumerable, then they are both recursive. And if, by the way, if L is recursive, then L minus is also recursive.
Right. And that was used to solve all of the problems that she listed for the home, for like the
Stop calling it homework. That stresses me out.
what do you want me to call it?
Exercises. We'll call them exercises.
The exercises. The
KSAS exercises. That's what we're going to call them. Yeah. Professor, I was looking at your recommended problems for the other day. Right.
So funny.
Because number 12 used it, number 5 used it. Just that theorem in particular was important to both the questions. So keep that in mind.
Okay, so Mr. Enumerable, is there anything else in that chapter you want to draw our attention to?
Let me check out the other, because I'm pretty sure there were 3. That was 2 out of the 3. I don't remember what the third one was.
By the way, this diagonalization proof is really dope. I really like that.
Don't even try.
No, it's really, really nice. I actually,
Yeah.
I took time to
Try.
understand it, and it's really so smart. It's so simple,
I don't have time
And
to
it's
take
so
time.
powerful, you know?
Okay, so I came across something when I was watching Easy Theory Guy on that. And he was talking about how you have your natural languages and your real languages.
Mhm.
And you can count your natural languages. You cannot count your real languages.
Yep.
So he says, so if we could list them all out, if we could list out like all of our numbers, if I got this right. Anyway, you could list them out. And then if you showed, if you put, like if you lined up the diagonal, which it's not going to, me telling you this here is not going to be as impactful. But if you could pick numbers that were in that diagonal space and pick some different number, then you're actually proving that diagonal is not in the element. It's just kind of fascinating.
Yeah, it cannot be because you just swap the bits. So it kind of
Yeah.
guarantees to you that it's not in any of those elements. Therefore, it has to be a new element. Therefore, by the pigeon principle, yada, 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 right?
Yeah, not in there.
No, that was pretty dope. I actually like that part. Okay. Next one. Prove that a problem is undecidable. I have no idea how to do that. I don't even know that.
This is one where we had to reduce everything to the halting problem.
Okay.
Can we just put a halt on the halt problem? Okay with that.
Let's just start with the easy ones because the next two are pretty easy. I mean, the last two, the NP complete, we know how to do that, right?
Hold on a second.
So
Let's redo that one.
we do anything reduces to a proxy, and then that reduces, this is NP complete, right? Okay, so this is the hash one. What's it called? The path, hash, sat path, whatever. I forgot
The,
name.
the Hamilton path, ham path.
Ham path, yeah.
Yeah.
Oh, so we need a list of problems which are NP complete. We know
Oh yeah,
that
okay, so ham path, the S3, hold on. I'll tell you
Reset.
reset
Click
and the traveling
CLIQ.
salesman problem. TSP is NP complete, right?
Yep. It's in the click CLIQ.
Oh yeah,
I think SAT was as well.
click or click. I like click better.
Yeah, I do too.
I like click more. I mean,
Well, I think we should just vote it and let it be.
Theorem 14.5 says a satisfiability problem, SAT, is NP complete as well. So SAT should be good.
Thank you. SAT, all right.
Yeah. So
Oh,
we got
actually, it has to be
reset and
because
set.
you can reduce them one to another, right? So
Yeah. I mean, what other things are there they could ask us for this? Book certainly doesn't list anything else. I mean, it says that the Euler circuit is not NP complete.
okay, so now how do we use them? The way you use that is your problem will be about this language in here, this one at the end. Then you have to show that it's NP complete. So you have to show that you can reduce a known proxy, i.e. one of those problems, into your problem, right? Or vice versa. No, this way. Okay. And then you just proven that it's NP complete. Call it NP complete proxy.
Yeah, I kind of feel like there's going to be like more of us describing and writing things out on this one. It's not quite as concrete. So I feel like she's going to be able to give us points if we can explain, if we can show that we can talk our way through it. I think even if it's not necessarily, you know, maybe her
Right.
words, I think she'll still give us partial.
Yeah.
yeah.
I don't think she has a choice, to be honest.
I don't, yeah, that was the one thing, like, I agree with what Tom, you're saying. You're like, she can't fail us all, but she's also not doing a very good job to make us feel like we can do it.
Mm-hmm.
Like, she's very explaining at us instead of explaining to us, and it's
Yep,
not
that's right.
working for
And
any of
she
us.
can explain to us because we saw her do that in the first, before the first exam.
But I think she focuses on those items that are really irrelevant. Like the other day when she was explaining to you guys the, what was that thing? Oh yeah, it was the NP completeness, and she said you can reduce from A to B and from B to A. Well, you don't have to go from B to A. You just have to go one way, and that's it. That ends the proof, right? But instead, she said, "Oh, we can also do this and do that," and then she just circled the first two things and said, "Actually, this is enough." That's. I think it's confusing more.
Yeah.
Right. So the problem. Okay. So the problem in the book, the one that we discussed with her, it was to show that TSP is NP complete. Right. So show that TSP is NP complete, and the way we did that is we basically had to represent a known NP complete problem. In this case, that was the ham path as TSP. Right. We were able to basically do that. I'm just going to write it here. We were able to define a function ham path something TSP. Right, this is the reduction. So that basically means that you can calculate this using that. And in doing so, we know that ham path is NP complete by definition or by the book. So any problem can be reduced to ham path. Now, since ham path itself can be reduced to TSP, that basically means that anything can be reduced to TSP as well, because you can reduce anything to ham path and then from ham path to TSP. Therefore, by definition, TSP must be NP complete. This is as simple as it gets.
Okay, so I understand that, but the process that she was going through to try to show the ham path was TSP or vice versa. I can't remember.
It was this direction. Because whatever you're showing is always going to, whatever the problem says that you have to show that is NP complete is going to be at the end of this progression line, right?
Right.
So
how
this,
would you show
yeah,
that TSP is reducible to ham path?
I would take ham path and present the algorithm for ham path using TSP and known shit like addition, subtraction, whatever, right? So this is our black box. We don't care how. We know that TSP is going to work. And I believe we did it before, but we can actually repeat that. The difference between ham path and TSP, if we were to, and guys, I like the Python or whatever programming language notation because it's easier to read.
Yeah.
Yeah.
So pseudocode. So let's get rid of Python. Let's just say it's a pseudocode. So what's the difference between?
Sorry, Tom, this is the same thing we do with the halting problem. You're just, it's the same thing. Instead of ham path, you would put halting problem, and we're defining it in terms of another function. So if we can do that, it's kind of like reducing it, right? That's what you're saying, correct?
Yep. So in C, if you were to define those functions, the difference between ham path and TSP, well, this actually takes an extra argument in K, right? Is that TSP requires a complete graph. And ham path works on any graph. And this was actually emphasized in the problem itself, that TSP requires the graph to be complete. Am I right? Can someone confirm that? What was the question? Yes.
Yeah, you're right.
Yeah, it actually says the traveling salesman problem can be stated as follows, blah, 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 let G be a complete graph. Okay. So if not for that, if TSP could work on a regular graph, then this question would be trivial because we would just say, okay, for a ham path, I run TSP on any K, like the K would be, in that case would be either a total of all edges, or I nullify all edges to 0 and run it like that, TSP, G, end of story, right? It's trivial because then if it works, if it returns a true, that means that there exists a ham path in this case. Right? But the challenge here is that the TSP requires a complete graph. Okay, so what she did, and what we should do as well in this case, is we're gonna make another graph. We're gonna call it proxy graph, right? And that's going to be transform graph to complete G, right? So basically, this is our pseudo function. This is our pseudo function. What it takes. What it does is it takes any graph and just returns a complete version of this graph where the original weights are 0 and the new weights are 1. It could be, doesn't have to be 1, it could be 75. All right, so if we have a graph like A, 3, B, 4, C, okay? In order to make it a proxy graph, after we run it through this function, it would be A, 0, B, 0, C, 75, A. Agreed?
Makes sense. Yep.
Yeah.
Right? Okay. So now what we do is we have this proxy graph, and again, the only reason why we did that is because TSP is picky and it requires a complete graph as an input. Okay. So now we say return TSP G. Sorry, not G, it's now going to be our proxy graph, 0. That's the end of proof. So look what we're doing here. We're saying, hey, Mr. TSP, is there a way for you to visit all the nodes in this graph in such a way that the total, that the sum of all your weights is going to be 0. It will not exceed 0. And this is a tricky way of saying you can only traverse through those original vertices. Because,
okay.
right? I heard that ding, 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 going off right now. This is just a way of saying you can only traverse through the original vertices because everything else has a non-zero weight. And TSP will not allow you to travel through that road. And that's it. If it says yes, there is a route ABC, which has a weight of 0. We know that this route must have existed in the original graph, right? Because if it didn't exist in the original graph, if that was a new vertex, a new edge, it would have a value of 75. But it can only follow the edges that have value 0. Right? So if it says, yes, there is a path like that, then we know that in the original graph, if we now were to go one step back, in the original graph, there must be a Hamiltonian path because we were just visited every single node using the original edges. And that's it.
And notice what he's doing, and it's the same thing with this halting process, is that we go from general to more specific or some form of restriction.
Yep.
If you can prove that it works in a restricted form, then it will work in the abstract general form as well.
Correct. All right. So now, that was the difficult part, understanding that everything else is just a wall of text. So now you say, oh, we have just proven that ham path can be reduced to TSP. Since ham path can be reduced to TSP, we say ham path can be reduced to TSP, right? And we know that anything can be reduced to ham path because ham path is NP complete by definition. Therefore, anything can be reduced to TSP. And if that's the case, then TSP must be NP complete.
So what? Can you say that again? Anything can be reduced down to ham path? Is
Yes.
What you're saying?
Yes.
I don't think he's meaning anything. He's just giving it an arbitrary name.
No, it is anything. Any NP problem can be reduced to
Oh,
ham
any
path,
MP. Okay,
Yeah.
gotcha. So
which basically means anything, right?
I'm gonna
Well, anything in the NP space can be reduced to ham path. This is by definition of NP completeness. So this is given. This part we've just proven, right? Therefore, we can remove ham path from the equation and say, okay, so any NP problem can be reduced to TSP, which is the definition, a textbook definition of NP completeness.
Yeah.
Okay, I got a question for you.
Go on.
Can we go through the question that talks about the traveling salesman? I'm not saying do it, and just tell me how you got, I know you didn't do it because she did it, how we're supposed to get this from the question.
Okay, I'll tell you how. There's actually hints in the question. I'm going to copy paste it here.
Okay.
This is the question. So it says the traveling salesman problem can be stated as follows. Let G be a complete graph, and complete is the keyword here.
Right.
Let G be a complete graph whose edges are assigned non-negative weights. The weight of a simple path is the sum of all the edge weights. I mean, we know that. The TSP problem is to decide if for any given K, so there are two givens for TSP, two arguments. There's the complete graph G and any given K, which is an integer, right? Mm-hmm. The graph has a Hamiltonian path. So the question quite literally gives us this. It gives us the API or the whatever you call it, the description of this function TSP. It tells you what are the inputs and what are the outputs. Now you recognize that, hold on a second, Hamiltonian path is also what HamPath returns as an algorithm. So they pretty much do the same thing. The difference between HamPath and TSP, apart from the completeness of the graph, is that TSP has an additional restriction that the total value of edges cannot exceed K. HamPath doesn't care about any of that. HamPath just says there's a path between those edges, right? Mm-hmm. So their functionality is very similar. So now what you have to do is you just have to get rid of this K. And again, if not for the fact that they have to be complete, I could say, let's just assume for a very second that HamPath also works with complete graphs. It's going to be easier that way. Complete graphs. All right, so we have complete graph here and here. If that was the case, we don't have to do this transform graph to complete K. We don't care about any of that. We then just do return TSP directly on G. And now you have to come up with K. What's the maximum K you can come up with? Well, that's going to be sum of all edges, right, as your K. So basically you're saying if TSP can come with any path whatsoever, no matter what the cost, then we know that there exists a Hamiltonian path. Hmm. And because we know that TSP nor HamPath cannot travel through the same edge twice, through the same vertex twice, then we know that this is the maximum K you can have. If you want to be super safe, you can multiply it times 999 or something stupid like that, you know? But
yeah, I think basically the main point is you just have to make up some kind of distinction that makes, you know, that narrows your TSP more than your HamPath. Like
the meat of this question is how can you express HamPath using TSP?
Yeah.
Right? If that, you remember those classes, the C++ classes, when some of the libraries would come up as black boxes. Like this could be a binary code. You might not have access to that. Sorry, that's not C++. That would be the comp.org, where you actually load something into memory that's a binary, right? You don't know how this function works. You just know that it takes two arguments and it returns something. Mm-hmm. So we don't care. And now I'm saying you have to use this knowledge to calculate that. And this is how you do it with those two steps. Right? So the implementation of TSP is irrelevant. And that's why I was arguing with her when she said that they have to be P or NP. I said, it doesn't matter. Whether this function and this function is P or NP is irrelevant. The only part that actually matters in this whole translation is that this translation itself is polynomial. And we see it's polynomial because this thing is just very simple. You just go through every edge and you replace the weight with 0 and then you add new edges. This is totally polynomial. And then you call this function. That's it. As long as this process of translation is polynomial, not the execution of TSP, not the execution of HamPath, just this translation, then you've proven the MP completeness. So if you want to be super strict, you actually have to say in this reductions that they have to be polynomial reductions, which is just, you just throw it as a word. Basically, if we can produce a function for it, it's a polynomial reduction. All right.
Yeah, that makes sense.
All right, so you understand how I got from the question to this, yeah?
Yeah, a lot better now.
That's really good.
Cool. I'm gonna get rid of this question because we don't need that. I'm gonna share this file with you guys. So do you want me to keep this code here, this pseudocode?
Yeah,
yes, please.
so.
All right. So that's the NP complete. It would probably be beneficial if we look up some examples of those other algorithms being used in reductions. Well, we'll have to just prepare that. We can have another call tomorrow and just review them quickly.
Yeah. I can't believe she got us through this whole book. I was just looking at that.
Yeah, she did.
Oh yeah, true.
How much do you know about 12.2 through 5 though?
Yeah.
I know their numbers.
Yeah.
That's all I know about it.
Hold on, what is that?
No clue. That's why I'm saying.
All right, so just a quick one. Show that the language is dtime. That's pretty easy, right? This basically just needs to, means that you have to provide a Turing machine, a deterministic Turing machine for that language.
Yeah, I don't think she's probably going to give us a hard one on that. I feel like
How many other things can she actually ask us? She's already asked us for, we got from the book straight up just 2 words put together. The example question had 3 words put together, and the other example question is 2 words.
Maybe she's gonna ask us 4 words put together. Right?
well, I was going to say where she could make that an extra credit question and give us something kind of really weird and creative.
I mean, the book doesn't do anything besides those, so
Yeah, you're
it would
right.
have to be really creative.
All right, here's the thing. We have to be able to type it in and submit it in 3 hours. But more importantly, they have to grade that exam within a week or something like that, right?
Yeah.
So
Right.
they will not want it to be too blown out.
She might give us that number 2, the one with the reverse in there.
Yeah, there's a WW reverse W.
Yeah.
We should do that one.
Yeah, I'm down to do it.
Yeah.
So what do you want to do?
Yeah, number
Done.
2, page 365. It says show that, okay, so this is the D-time one where you have W.
365.
Mhm.
Okay, W minus W, yeah, this one.
And I would bet you money that'll be an extra credit one there.
I don't think it's an extra. I think it's going to be
It
a
could be a
regular credit.
mandated.
Yeah. All right.
This screams 5 points to me, so I'm with Wendy on this one.
Put some bets down.
Yeah.
Send me chocolate if I win, y'all.
I mean, this is pretty much exactly what our homework question was. We had www, or was it a discussion?
Yeah, but this has a reverse in the middle.
So
Yeah.
you just change the state. You flip the state. All right.
Well, so
You're saying-
previously, in our previous examples, what we basically did was we just looked for the dividing points between W.
That's
Like,
exactly what we're going to do. So let's say we have our tape 1. We have some characters there. I'm going to use 9 as an example because it's easy to think about it.
Yep.
So first we have to put the length of the word on tape 2, right? So we do the same thing. We're going to do boom, skip 2, boom, skip 2, boom, skip 2, right? So then we start at 3. We're happy with the number 3. What we're going to do now is we're going to...
Wait, I was interpreting the way that they were writing this as like word was 1, 2, 3, then word reverse was 3, 2, 1, and
That's
then
right.
word
That's
again was
right.
1, 2, 3.
Oh, sorry, you're right. Yeah, you're right.
Okay.
I actually didn't realize that I didn't put...
Okay.
You know what? I actually, that was I put the numbers for the cells, but we don't need those. So you're right. Yeah. Okay.
Right. Okay. Just want to
All
make
right. So here's the algo. You ready? So the first run is you put those 3 digits here.
Yep.
Right, to get the number 3. Then you reset headers, and you extract W itself. So you put it here. Just for clarity, we put it on the next tape. Right? Easy so far.
Yep.
Right, so we know that this and this is the same. Correct?
Yep.
All right. Now you put this header at the end. So tape, if it's tape 1, and this is tape 2, and this is tape 3. Okay, so now you put your header at the end here. In here, you're here, and you know what we're gonna do, right? So for every one, and here, you put your header here, and for every one on tape 2. So basically, you always use tape 2 as a counter, nothing else.
Yeah.
Okay, so now you do compare this with this. So this header goes to the right, this one goes to the left, this one goes to the right. All right, it matched. Then another tick. I'm gonna stop drawing it here because it just confuses the shit. So 2 is equal to 2, so we're happy. And then you have 1 equal to 1, so we're happy again. So basically the headers go in different directions on tape 1 and tape 3.
Gotcha.
And-
So you're comparing heads to tails going
Yep.
in opposite directions.
And now you reset, I mean, you know what we're gonna do now, right? So you reset the counter, which is T2, and you compare sequentially T1 and T3, and that's it, end of story. We've just proven that we can produce a deterministic TM or whatever, blah, 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 all that bullshit.
Okay.
So the only tricky part here would be because we could do a tape 4 and copy that third part over, but it's still that's no
Why
different.
would you use a tape 4 here?
Because that's the
compare-
way that we learned.
Well, no, but to compare parts 1 and part 3 together to make
Yeah.
sure it's right.
You don't have to do that. Your T3 is your W.
That's right. You're right. But don't you have to compare it with the part 3 to make sure it matches? I mean, I guess
No,
you could.
I said we do that.
That's
After
right,
we're
that's
done with
right.
part 2, it's just a sequential comparison again, right?
Yeah, I got you. You're right. You're right.
Once you extract W here, it doesn't change. And
Just
this
let me
doesn't
do it
change
the
either.
long way, Tom. I'm just
I
kidding.
don't
No.
understand even what you use the tape for. Like,
It's-
honestly, I have
No,
no idea.
no,
what you
you're
use.
right. I mean, I wasn't thinking it the right way through. You're
I'll tell you
correct.
right now, because this is the way that I've been thinking about it the whole time, is we take the first 3, we
Okay.
split the T1 into 3 different strings. We put the first 3 digits on T3, we
Yep.
put the second 3 on T4, and then the third 3 on T5. Then we can compare T3 and T4, T4 and T5, make sure they're all the same.
You understand that you can blow any algorithm into 50 tapes. You can say, I'm going to put random characters on tape 275, you know?
Then that's what I plan to do.
Okay.
You just refactor faster than the rest of us, Tom.
No. It's actually easier that way because look, well,
Yeah,
Let me
yeah.
just- let me just point one thing. The actual comparison run, from the point of view of tape 1, you always go to the right.
Right.
When we actually compare, here's what we do. The first 3, we don't have to compare because we put them on tape 3, right? So as soon as we finish putting them on tape 3, our header is here.
Correct.
Okay, now we put our tape 3 header here. And again, we keep progressing on tape 1. So we go here, here, and here. And here we go in reverse, and they match. Right,
Mhm.
now we reset tape 3. All we have to, we actually don't even have to reset it because it's there already, because we just finished the tails
Yeah,
to head
the
run.
header's already back at the head
So
again.
it's already there, and you just continue. 1, 1, 1. That's
Yeah,
it.
that's very good.
Tom's trying to find a new efficient way to do this.
This
but we
is
still don't
actually
even understand
easy.
what's going on.
This is actually easier than www. You know,
It is. I'm so used to comparing instead of thinking about moving the heads and tails in different directions. So
Yeah.
that's a good practice.
Cool.
Yeah, good job.
See, I'm not even thinking about this as having a header at all. I'm just like, yeah, we're splitting it into strings, then we're good.
Mm-hmm.
Because that's the way the textbook is like, yep, we just kind of split it up. If it's
And-
not the
and
same
that's
length,
that's a
then
big mistake they're making. The emphasis should actually be on the header because it makes it so much easier when you think from the header point of view,
does.
right?
Just watching
then-
how you've done it a couple times now.
Then you kind of try to explain to the header which state are you in. You're doing this. Okay, why are you doing this? What's the next thing going to be? You know, and that's how you get the mental picture of what the states are going to be, and then you just reduce them.
The thing at this point though is I don't think I care really. I'm just trying to get this done. So
Fair
it's
enough.
a thing of, okay, the book is telling me I need to just
Look, you can
focus
do
on
it.
this.
You can do it with five tapes, and you still
Yeah.
get full score for that. I'm sure. It's just easier, I think, with 3 steps.
Just blow it up, Caden. We're all supporting you.
I mean, just think about the number of rules that you have to type for those 5 tapes versus what we
Yep.
get to type for this one.
It is more to
Yeah.
keep up with the more tapes you have.
Maybe.
It's not always. I mean, in some cases.
Depends on how you describe it, yeah, because if I'm just saying like I'm not keeping up with the tapes, I'm kind of ignoring 1 and 2 after I've already done
Yeah.
after I've split them off into the 3. And how the thing that I was getting emphasis from in the textbook was that at each step we had to make sure that we were saying, well, this is an O of W time to make sure that it was polynomial reducible or whatever the hell they were talking about.
At no point we had to do something like for 1 move of tape 1 we do like full sweep of tape 3. That would be n squared.
Yeah.
And actually, there was one case when we had to do it, and we were doing the power machine, but that's kind of obvious that you have to, right?
Yeah.
So,
Right. As long as you're doing a 1-to-1 correlation, you're still in time.
correct. It doesn't matter how many times you bounce them back and forth, as long as you always move them in sync.
Yeah, because you could run over the whole string 5, 6, 7 times.
Correct.
That's
But note, the
really
key
gonna-
was that our tape 2, which is the counter, it always ticks. It never stops for a full run of another tape, because if it had stopped for a full run on another tape, then you're looking at n squared.
Yeah.
And actually, the n over 3 squared, but it's still n squared, because that'll be the, yeah. Okay.
Capital. Got that. What is that? Pride and Prejudice in my mind.
Right. Decidability, I have no clue about that.
Let me go back.
We're reducing to halting problem every time.
And that goes right back into what we just did with what he did with the hand
The
path.
ham path, yeah.
Take your generalized halting machine, and she gives you some restrictive form of a Turing machine.
Was it like something that we did on the actual homework? Hold on a sec. We did
Yeah,
something.
what
we
was
did
it?
12.1 number 4, the general halting program.
Oh yeah, 12 final. Yeah, okay. Yeah, that's easy.
Yeah, it's easy.
I mean, it's easy in, like you said, it's the same thing. We use the same trick. It's all about being able to represent one machine or function using another machine or function.
Yeah, so in this case, we kept
I
the-
personally,
Sorry.
I was gonna say, I personally wouldn't mind running through this if anyone else wants to, but if no one else does, then we don't need to.
Please do.
Yeah, absolutely. Let's do it.
Let's do that. All right.
The more we do it, the more comfortable you get with me.
Her explanation sucked.
Well, she
Yeah.
I don't know.
The explanation she was giving me was using the state entry problem and then running into the halting problem, and then by that you prove by contradiction that, like, you know, it's undecidable or not. But
Right.
then she said, "Oh, it's actually simpler than that." But
Yeah,
that
we don't share your hard-on for state halting state entry machine or whatever. So I don't even know what that is.
yeah,
It's another one that's known as decidable. So
Yeah, but
you
okay.
throw that in there every once in a while if we need
So
to.
we're looking at question 4 from the homework. Yeah.
The
Alrighty.
algorithm that works for all M, but only a single W.
What does that even mean?
Oh, okay. That's the one where I was trying to say, okay, functions. Okay.
Yeah, because it's decidable if for every W there exists
All right.
a possibly different algorithm.
So let's just read the question. It says, in the general halting problem, we ask for the algo that gives the correct answer for any M and W. So basically, we have a function G that takes 2 arguments, M and W. And we can actually write the code for that. The pseudocode is going to return 1 if M halts on W, else return 0. Right? Do you all agree?
Yes.
Agreed.
Cool. Now what they're saying, and it's probably not the best language to use, they say we can relax this generality, for example, by looking for an algo that works for all M, but only a single W. So what they're saying is we're going to have a specific function that only takes 1 argument, M. And the W is going to be inside the code of that function. So return, it's going to be the same body. It's going to be the same body. But the difference is, whereas here W was an external argument, in here it's hard-coded. And a nice way of representing that is let's put that W in the name of the function. All right? And you can think of that, she used the print example, so we can use the same. Let's say you have a general function that says, say something to someone, right? Something, someone. And then we just do print, hey, someone, here's something, Obviously that wouldn't work because of the quotes, but whatever. Like, and so this is our general function. This is our general problem. It takes 2 arguments and it works. Now we're saying we're going to use a specialized function which only works with one person. So it's going to be say something to Wendy, something. Okay, and it's always going to say print, hey, Wendy, here's something. So this is our general function. This is the specialized function. Trivial for now, yeah?
Gotcha.
All right. So what they're saying is we know that this general halting function does not exist. We know this because if it did exist, we would live in a completely different world. So this does not exist. Right? Because it's undecidable.
Yeah.
What they're saying is show us that even this thing is also undecidable. Prove that this does not exist either. Okay. So in other words, just imagine for some weird reason we cannot print anything on your screen. So we're saying, hey, we know that this doesn't exist. We cannot just print, hey, Wendy, here's a cat, right? But we're saying, okay, but what if it only works for Wendy or if it only works for Mark, right? Can you then say something about the generalized problem? You can see where we're going with that, right? If you had the family of functions like that, say something to Wendy and say something to Mark and say something to Tom and say something to whatever, then what you can do is you can say, okay, I can actually rewrite this generalized function to use this array, this infinite array of specialized function to achieve the same goal. All right, so in here, rather than doing this print, I can rewrite the same function. I'm going to keep the original code. And I can instead say spec function is going to be find function for name someone. Okay, this thing is going to return, say something to someone, right? Whatever the someone is. Mm-hmm. And then I'll basically call it spec func something. Right? Those 2 functions are identical.
Right. The only thing is with the second one, we're assuming that we have a whole bunch of functions.
Right. That's very important what you said. We don't have to assume that because the problem says that. It says, quite literally, and I quote, we say that such a problem is decidable for every W. So basically they're saying that for any someone that you provide to say something to someone, there's going to be a specialized say something to someone, so say something to Wendy, and say something to Mark, and so on and so forth function.
Huh.
The problem basically says this is guaranteed. There is going to be this specialized function. Okay?
Okay.
You'll follow?
I'm not necessarily following on this one.
So if you could create a function that would figure out how to specialize it to me, then you would be able to write a general function that could specify it to anyone. So what we've just done in doing that is we've taken one function and applied it to a family of, or applied it to multiple. Am I saying this right?
Yeah, I mean, imagine that there's only 2 names in the whole world. Let's just narrow down the scope of who someone can be. Let's just say that we live in a world like communist China where only 2 names are allowed. Wendy and Mark.
Chinese
right? we have to narrow it down somehow, right? So let's say there's only 2 names in the whole world, Wendy and Mark. So now we have something to Mark. Hey, Mark. Here's something, and I'm going to rewrite this so there's no find function for name anymore. It now says if someone is Wendy, not return, then call say something to Wendy something. right? Else if someone is Mark, say something to Mark something. Okay. Do you now agree that in a world when someone can only be one of those two values, those two functions are the same?
Yes. Yeah.
Good. So if those two functions are the same, well, you just finished, right? You're done, because we know that this function cannot exist. But they're saying, okay, what if these functions existed? Well, we're saying if these functions existed, we can rewrite this function as those specialized function. And we just reach our contradiction. We actually use the same name. So even the compiler would say, hey, you have two codes for the same function, right? If this function, so we take something that we know exists. This is guaranteed by the problem. They're saying for every name, for Wendy and Mark, there is going to be say something to Wendy, say something to Mark. So this is our assumption. It says for every word there exists a function. So we've just redone our generalized problem using those specialized functions. Those two functions are equivalent. They do exactly the same thing. There's no difference between those. So if those things exist, then this must exist as well. But it cannot exist because it's functionally equivalent to something that we know that doesn't exist. That's your contradiction. Therefore, the only explanation is that those functions, say something to Wendy and say something to Mark, cannot exist either. Because had they existed, then this general function would also must have existed. It must exist at that point.
And I don't know, this may be throwing you off too, Matthew. It kind of did me a little bit, but where he's got Wendy and Mark, just picture an infinite number of possibilities.
Yeah, this would be your W,
Yeah.
right?
So what happened to me was I'm sitting here thinking, well, I think we can do those specialized functions. Why can't we figure out a program for even numbers, right? Like why it seems feasible. So therefore it seems like we should actually be proving that the halting problem is decidable, but you just gotta get that out of your mind. For the test, none of this is decidable.
Yeah, but in this case, in case of this question, right, we have to explain it in mathematical terms and whatever, but the general idea is as simple as that. So going back to where we were, we have our general halting problem that takes M and W. This is the way it works. They are saying that for every W, there exists our say something to W function, which is our specialized function that only takes M as an argument, which would be the something thing here, right? And basically what she did with this whole find index of, she basically saying that this G can be now rewritten exactly as we did before as find the SX function and then return for the SX function for W, which is guaranteed to exist, and return SX of M, right? And if they're saying that this family of S functions exist, then we can rewrite the function that's supposedly impossible to achieve like that. And this is guaranteed to work. So if it's impossible to exist, if it's supposed to not exist, and we've just proven that it exists, if Sx exists, therefore those functions S must not exist. That's your contradiction, right?
Yeah, and you have to always keep in the front of your mind that your ultimate goal is to prove by contradiction.
Yeah.
So if we start with the general and we try to rewrite the general and specific, then what that means is that if we could do the specific, then the general could be done. And we know that the general can't be done. So therefore, by contradiction. Yeah,
the key here is that specific is going to be, well, like the word says, it's going to be specific to just one particular case. So you will need the infinite array of all those specific functions to generalize it. Like in our case, infinite means 2 because we assumed that the domain of someone is just 2 words. But it could be 50 or it could be infinite. It doesn't matter as long as you know that you can produce that specialized function for this particular argument. And the problem must state that you have to, because otherwise you won't be able to prove the contradiction. All right.
Kind of got a question.
Yeah, go
on. I'm kind of getting stuck up on the language when they're talking about the halting. So return 1 if M halts on W. In
Yeah.
our case, halting would just be finding the function and printing it out.
In our case, okay, so how this S function or the G function implements this test, we don't care. This is, again, this is black box for us. We don't care. It will set up a test sandbox. It will basically feed W to M and see if it halts or not. But how it does it, we don't care. We don't care about anything. We don't care whether it's NP, whether it's P, whether it takes 5 million years to complete. We don't care. Because those functions, they do exactly the same thing. The only difference between them is this function, the general function, can do it for any given word, and the specialized function can only do it for one word. Right? So in order to generalize, you will need a complete array of those specialized functions, just like we had here. Say something to someone works with anyone. But say something to Wendy only works with Wendy. Say something to Mark only works with Mark. But since someone could only be either Wendy or Mark, then we can say, hey, if someone is Wendy, then just pass that something to say something to Wendy.
Right.
If someone is Mark, take that something and pass it to say something to Mark. So those two functions are exactly the same thing. In fact, if you compile them, you'd probably end up with the same machine code because the compiler would optimize your code. So those two functions do exactly the same thing in this realm where someone can only be one of two things.
And when you're saying, when you rewrote the general halting problem, find the SX function, X is just an array, not an array.
No, SX is going to be one of those S functions.
W's.
For that given,
okay.
Yeah. What she did, just so you understand what she did in the video, so you don't accuse me of giving you false information. She basically said that there's going to be some kind of index. So find the index of the S function, right, for W, which is the same thing as saying find that function. I don't think she would take your points for that. She did say that you have to show that it's always possible to find that index. I say it says so in the freaking question, where it literally says, we say that such a problem is decidable for every W. But where
I'm just looking to keep it as least complicated as possible to try to get whatever credit I can get at this point.
If you wanted to, if she were to take 1 point for that, excuse me, the answer to that question is that W has to be in some kind of a enumerable language. Therefore, you can provide the index for any W, something that Wendy mentioned before. And I said, this doesn't make any sense because you would have to have the complete dictionary to know exactly which page to open that dictionary on to pinpoint the
oh, I see what
word,
you're saying.
right?
Okay.
Yeah. But again, this part is not that important. What is important is that you will always, as the problem states that, you will always be able to find which function that is. So in other words, you know that if someone is Wendy, you have to say something to Wendy. If someone is Mark, you know that you have to say something to Mark. If your W is ABC cat, you have to use the function S that does return 1 if M halts on ABC cat, right? So rather than having one function that can accept any number of W's, you have any number of functions that only work with one word.